In a part B, here the region of this between the plate is now filled with the material having the dielectric constant of 5.6. You introduce a dielectric material now. What is the capacitance value? In the part B, if you introduce a dielectric constant of a dielectric material of dielectric constant of 5.6, what is the mean value of the capacitance? C prime is what? I already wrote the formula. C prime should be equal to alpha times C. All value is given. So it will be 5.6 times what is the value we have? 50 picofarad. Picofarad. Whatever the value you get, that going to be, like that. Very simple. Any question about this one? I didn't go through the calculation, but you should be able to get the right answer. Okay, it's a minor thing. Okay, I'm gonna finish. Like this capacitor. We're gonna talk about more about the circuit. So if you have a more than one capacitor, you can connect the capacitor in a circuit different ways. One is called parallel combination, and another one is called series combination. So let's talk about that. In electrical circuit, a capacitor is represented by a symbol like this. I mean, the symbol is like this. Okay. In the electrical circuit, you have symbol like this. Okay. This is a capacitor C. The capacitor having the capacitance of C. Okay. The symbol for the capacitor. And we're going to talk about resistor also. A resistor can be represented like this. Okay. Some of you guys already know. A resistor of a resistance R. And if you have a battery is represented by this. One is longer, positive terminal is longer, negative terminal is like that. Okay, it's a symbol that in the electrical circuit. Sometimes students get confused between battery and the battery. And this is the capacitor. And this is the resistor. Sometimes students they confuse about this one because both look like a two lines, but the battery you have one line is longer than another one. Okay. So in the capacitor both lines are equal. Okay. So this is how you represent in the electrical circuit. Now, so if you have more than one capacitor in a circuit, we can connect them in two ways. One is called series combination or configuration, and another one is called parallel configuration. Okay, let's talk about that. So let's talk about series and parallel. So this is the one of the ways that you can talk about it like just two. I mean, if you want to make 2, 3, that's also fine. Make it a loud. Right? What is making loud? So you have a circuit where you have a battery that provides the the current that has an EMF. You have two C1 and C2. You have two current and two capacitors C1 and C2. Okay? If you connect two capacitor in a circuit like this, this is called current pass through this one, and it basically goes like this. Okay, it's called series configuration. Series configuration. Okay, or series combination. Okay, combination. There's another way that you can connect. You have a battery and you have combination like this. So you have a C1, this is C2. Okay. Now, the battery always provides the current to the circuit. But once you reach over here, the current will divide. Okay, we'll talk about this one. This is called parallel combination. Configuration. So there are two ways that we can connect two capacitors. One is called series combination, another one is parallel combination. It looks like very obvious that the current, the same current pass through this one, through the C1 and C2, okay, and it comes back. It makes a loop, okay. So here you have two capacitors. They are connected side by side. But here you have a battery. You have positive terminal of the battery, and you are connected like one side is connected like this, the same way that you have a same connection. It's not side by side connection. Okay? So this way, whenever you connect the capacitor in the parallel configuration, the current through the capacitor won't be same. You have an I2 current over here, I1 current over here. The current splits over here whenever it reaches this junction over here. The current through the capacitor won't be same. Okay. Let's take a look on some of the way that we can simplify this circuit, because in the circuit, if you have too many components, it will be always difficult. Okay. So one of the way that we want to simplify is that so instead of putting like this two capacitor, in the circuit, I want to replace with a single capacitor. Okay. Same way, I don't want to have too many components in the circuit. Like that. So this is called equivalent circuit. Let's talk about that. So at this moment, I have only two components. You can have like multiple capacitor. You can have 5, 6, 7 capacitor. Okay, it will be really difficult for you guys or for people to understand how the circuit is working. So one of the way that to simplify is that we combine all of the capacitor. Okay, like this. So if you have in a series configuration like this. Okay, you have a C1 and C2. Okay. You know, I want to simplify this one. In place of two capacitor, I just want to have a single capacitor in the circuit. But this new capacitor I put in place of two capacitor, it should represent this two. It's called equivalent capacitor value. And this circuit is called equivalent circuit. This circuit represents this one. Okay? Just simplify the too many components in the capacitor over there. So if you have a combination like this, the equivalent capacitor value, you can calculate that 1 over C equivalent equal to 1 over C1 plus 1 over C2. You can use this formula, and you can even derive this one later on, that we can get the equivalent capacitance like this. Okay, if you have a series configuration, you can replace a capacitor having too many capacitors with a single capacitor of the value C equivalent, and you can calculate the C equivalent like this 1 over C1 plus 1 over C2. If you have more than 2, you can keep on adding 1 over C1 plus 1 over C2 plus 1 over C3, and keep on going. In a circuit, usually there are so many capacitors. Okay, so the circuit diagram will be really big or like really massive. We want to simplify that one by just representing the circuit with the equivalent capacitors. This is for the series. The same thing you can do for the parallel. The parallel has a same also way to represent. So you have battery and you have capacitor. The battery provides the current, it's a power source, okay? Without battery, there's no electrical circuit at this. And battery is the one that is the supply, the power, okay? The C1 and C2, you can represent C1 and C2, okay? So similarly, putting like too many components in the electrical circuit, that's not good. So we want to represent the same circuit like this. In place of C equivalent, I just put like this simple circuit. Current I is passing through this one. I have a battery of EMF E. Take a look on this one. This is an equivalent circuit. So in place of making like this figure, we can use the simple figure like that. This equivalent circuit and this equivalent circuit look same. Okay? But it looks same. The current looks a loop over here. But here, the way you calculate the equivalent capacitance is like this way. And for this, The equivalent capacitor is given by C equivalent. C equivalent is just like simple C1 plus C2. In the parallel circuit, it's very straightforward to find the equivalent capacitance. We can derive this one. I mean, you can see in the slide, you can easily derive these things. We can do one of the derivation, either series or parallel, whichever you want me to derive. It's not that fancy derivation that we cannot do it. So one of the things that I want to point out over here, having the capacitor in series and the parallel, they have some different properties, and I want to write down over here. Those are going to be in your true and false multiple choice question. So let me list those very important piece of information over here. Let's say if you connect the capacitor in series, and for parallel, these are like two different way to connect. So one very important point over here is that if you have a capacitor in parallel, let's say you have a battery that provides a 1.5 volt, 1 volt across this terminal. This terminal is same as this terminal, and this terminal is same as this one. That means this terminal is same as this one. What that means is that the potential across the each capacitor connected in parallel is same, and that is equal to the battery potential, because this point is same as this point, because there is no component in between in the circuit. If this is 1.5 volt, this is going to be 1.5 volt, this is also 1.5 volt, and this is also going to be 1.5 volt. So that means the potential across the capacitor is same in the parallel configuration. Okay, I'm going to put down that one over here. I mean, potential is same. The potential across each capacitor connected in parallel is same. Same value. So whatever here in the series, but the potential it won't be same. I'm going to erase this one, that's too much. Okay. So over here, let's say C1. It has the same charge stored over here, Q. Okay, Q. And you have a potential is V1, which is equal to C1Q, okay, and V2 will be C2 times Q, okay. Although they have the same charge stored in the capacitor, you have a different potential value. So V1 will be stored in the C1, and V2 will be stored in the C2. So the potential across each capacitor connected in series will be different. So what is the very important difference between the series and parallel configuration, that you have capacitor in series and parallel configuration, and V1 potential drops across the capacitor C1, and V2 potential drops across the capacitor C2. Over here, since you have a same like a terminal goes over here, there is no electrical component in between. You have a same potential across each capacitor. The charge is going to be different over here though. So you have the same charge Q stores over here. Q is the charge. In C1, you have the same charge over here. The charge. So you have a charge. The charge. That will be same on each capacitor. Over here, the charge is going to be different over here. So since the charge and the capacitance value is related, Q equal to C times B. Okay, so Q is going to be C times B. So over here, you have a Q1 charge is C1 B. All the potential is same. You have a different charge C2. You have a different charge. Okay, charge will be different. The charge on each capacitor connected in parallel configuration will be different. And another important difference, I already wrote that I can derive this on later on. There is no way that I just leave without derivation. If I want to find equivalent capacitance, you do the 1 over C1 plus 1 over C2. You keep on doing, okay? So you can keep on, like adding. But if you want to find the net capacitance or equivalent capacitance, you can just simply add C1 plus C2 plus C3, or keep on going, okay? So this is the difference between the series and parallel configuration of a capacitor. So this is going to be very important for your true and false and multiple choice questions especially. The capacitor in the circuit can be connected in two configurations, and we can simplify by just putting a simple equivalent circuit. But whenever you calculate the equivalent circuit, you need to calculate this equivalent capacitance. So let's talk about how we can derive this formula. So let's say you have a capacitor in a series configuration like this. Okay, we can easily draw this diagram. I mean, it's easy diagram. You have a circuit, okay, and you have two capacitors, C1 and C2. A series, okay? The current I flows this one, and over here, we make sure that they are almost the same length, otherwise they think that we have. The current passed through this one to the circuit, but there's a potential drop across this one. The potential drop across this one is V. Q equal to C times B. If I want to find a potential, you have to have Q divided by C. Okay. The potential drop across this capacitor is V1, which is going to be Q divided by C1, because you have the same charge stored on each capacitor. The potential drop across the capacitor C2 is going to be Q divided by C2. You have a net potential over here, that is drop across over here. V1 and V2. So net potential, you can easily write down net potential should be constant. We can call this is the net potential E. It's going to be V1 plus V2. Right? There is no way that you lose the potential over here. It should be same. So use the Ohm's law. I think we're going to talk about Ohm's law later on, but Ohm's law over here, V equal to IR, or V equal to, let me see, let me do a very different way. So E equal to V1, just put the value of Q over C1 plus 1 over Q over C2. Q is common. You have Q. You have 1 over C1 plus 1 over C2. You are almost there. Right? So over here, I can write a E equal to Q times 1 over C1 plus 1 over C2. So what I'm going to do, since the potential E is equal to Q over C, what I can do, Q divided by C equivalent. This has the same form as this one. The potential is equal to 1 over Q over C. The potential is Q over C equivalent. Right? And if you get confused with this one, you can even just simply write a battery having the potential V. It's the same thing. The potential V from the battery. Nothing. Now, V equal to Q over C, V equal to Q over C equivalent. But here, this equivalent capacitance is 1 over C equivalent equal to 1 over C1 plus 1 over C2. What that means? A circuit having two capacitors can be replaced with a simple capacitor having the equivalent capacitance of C equivalent, and you can calculate this C equivalent by 1 over C equivalent equal to 1 over C1 plus 1 over C2. So this means I can write this one the simple circuit that has battery. Just put like a V, but you can just write it. But this capacitance is going to be this is called equivalent. This is how you derive. It's not too difficult. Similarly, you can do for the parallel. The parallel has a C1 plus C2. So, that is easier. Any question about this one? Okay. I think we have a couple of points over here. It's very simple that if you have more than two capacitor, let's say you have a 3 capacitor and they are connected in the series and parallel, what going to be the net or equivalent capacitance? It's a very simple problem over here. Let me show you over here. And there will be one comprehensive problem. I'm gonna talk to you guys later on. This topic is a little bit difficult for you. Okay. You have three capacitor. I just put like a C1, C2, C3. C1 equal to 1 microfarad. C2 equal to 5 microfarad. C3 equal to 20 microfarad. And it's asking that what is the total capacitance? Some people say total also. It's the same thing as the equivalent capacitance. If they are connected in series and they are connected in parallel. A series. If I have a series, then I just put like a 1 over C equivalent. It's 1 over C1 plus 1 over C2 plus 1 over C3. You have given the C1, C2, and C3 value, right? Just plug it over here. And if B is asked to find what is the equivalent whenever you have parallel. And this is also very simple because the C equivalent is given by C1 plus C2 plus C3, C1 plus C2 plus C3. And the parallel one is very easy because you can just add it. 1 plus 5, 6, 6 plus 8 is going to be 40. Okay? In the exam, some of the question will be like this. Hey, you have a 3 capacitor, then what is going to be the net or equivalent capacitance if they are connected in series? You can just use this equation. And the equation will be given in the exam. You don't have to memorize this one, the formula. Okay? This is simple one, and I might have a little bit complicated this one. Okay? This is a little bit tricky. You have 3 capacitor over here. Assume that C1 is 10 microfarad, C2 is 5 microfarad, and C3 is 4 microfarad. I want to find what is the equivalent capacitance of it. This is a little bit difficult than the previous problem. What do you think? How I can? So let me draw this one. You might know already the answer because so we have given the capacitor like this. The combination like this. You need to find. So B is a battery. Let's say you have a battery and potential. You have some potential coming from the battery. V. Okay. You have 2 capacitors like this. There is one capacitor. I think I gave this problem in one of the tests. So likely, you might get this one. And they have given C1 value is 10 microfarad. C2 5 microfarad. And C3 it is 4 microfarad. Now, my question is that what is C equivalent over here? This is a little bit tricky, and you need to know how the capacitors are connected. So you have the two formula which will be given in the exam. For the series, I can use that formula. 1 over C1 equal to 1 over C1 plus C2 plus C3. Or for the parallel, you have a 1 over, C equivalent equal to C1 plus C2 plus C3. Now, which formula you will use and what is your idea? It's a discussion class, I really encourage students to discuss during the class. It doesn't give any bad impression, right? Yeah.
Wouldn't you add C1 and C2 in the series and then add C3 as a parallel?
That's very interesting. Yeah, that's what you have to do. So here it's a little bit tricky because take a look at this one. You have a battery. C1 and C2 they are connected in series. Once you get some like a combination around here, this let's say you have a C prime. The C prime and C3 going to be in. So you have to use both formula over here. Let's try to find C prime from here. To find the C prime, because C1 and C2 they are in series. If you have a series, I just use this formula. It's over here. I'm a bit lazy over here. So the series, I just use this formula. So you have C1 and C2 in series. I just use this formula. You have one. Once you combine, I just put like a C prime as a 1 over C1 that is given 10. I just remove microfarad because I want to make my work very neat and clean. And C2 gonna be 1 over 5. Now you know how to combine this one. 1 over C prime equal to so you have this common factor is 10. 1 plus 2. Okay, economics 3 over 10. 3 over 10. Now if you want to find C prime, because it's a 1 over C prime, you need to flip on the other side. C prime gonna be 10 divided by 3. I know what the number you're gonna get. It's gonna be microfarad. Now, so once you get C prime, the C prime and C3 they are in the parallel, right? So use the equation of parallel. I just use this one over here. So this is for the series, and the formula for the parallel is it's a simple formula. C equivalent equal to C1 plus C2. I just have it's a formula, and I replace the C prime with the C3. Okay, C prime is like a 10 over 3, and plus you have a C3. That value is 4. And you can just use like calculator. There is nothing that goes wrong. 10 plus so 22 divided by 3, it will be 7.3 microfarad. I know what is it? Yeah, 7.33. It's gonna be, I just take one decimal place up, right? So you don't use your calculator, because this is simple addition. And this kind of question you might see in the multiple choice question. Definitely.
Do you have the notes? Do you have the notes? This time?
Any question about how we can connect MCD parallel configuration and capacitor? One thing I want to point out, definitely you did pretty much like a more improvement in the test too. Now we're going to focus on the final, and the final is going to be cumulative test And the final week gonna be crazy week. If you are unlucky, you're gonna have a 2 and 3 finals on the same day. So please, focus right now. And the content we are discussing right now gonna be a little bit challenging. This is not easy topic. So we already finished the easy topic, and the content we're gonna discuss from now on gonna be really difficult. Circuit and blah blah. There's like a electric field, magnetic field. Electromagnetic induction. Those topics are not easy. Okay. So I really suggest you to focus from now on. Okay. Anyway, so now let's go to the another topic from chapter 26. We talk about the current and resistance over here, and I'm going to discuss about the electric current in a microscopic level. So this is like an electric current, you might already know the current.
Oh, this is for
But
series.
I will talk about what is the current and its microscopic origin inside the wire. Okay. If you have an electric wire, this wire can be made out of copper. We commonly use copper or like wood, metal, platinum, or some other way. So how the current flows over here. So this is exaggeration. Let's say you have a wire, but I zoom like a much over here so that we can see everything over here. Let's say this wire is made out of sodium. You can have a platinum, you can have a copper. So any wire, it's a conductor, and you have a free electron. Free electron coming over there. I just represent it like a dot sign. And there are so many free electrons, and this wire is made out of like a many electrons. I just draw some of them. A dot line over here, and it's an electron. This is the charge carrier inside the wire. Over here, the electron, basically, it's like coming from the atom. And you might already know, and I might have already discussed about that. If you consider a sodium electron or sodium wire, so the sodium is like in the group 1. You can see the periodic table there. The sodium symbol is Na, sodium, and it has atomic number is 11. That means you have 11 electrons, you have 11 protons. Okay, and so proton is positively charged, and atomic weight is electronic 3. So the neutron is 12. So that if you have an atomic structure, you have 11 proton and 12 neutron, it makes 23, because in the atom you have, the mass of the electron is very negligible. So basically, the atomic weight is basically sum of the mass of the neutron and proton. Okay. Over here, if you consider like a cell model, how the electron is distributed inside the atom. My drawing is not that good. So basically, you have many cells where the electron distributed inside, in the atom. The first cell, it has 2 electrons, okay, and the second cell, my drawing is not that good. I want to make it a little bit better. Okay, 2 electrons. You have the second cell adding for the 2. You have 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. So 8 plus 2, 10 is already gone. You have another cell that is like outside, and this is the outermost electron. This one electron is a little bit far from this positively charged nucleus, so that's a loosely bound, right? It's loosely bound, and if you have a metal, or if you have any wire made of sodium atom, this electron is loosely bound, and it can flow freely in the wire. So this is how you get a nearly free electron in the wire, and this electron can take part in the flowing the current from one place to another place. Now, let's take a look. The electrons are always in a motion. They are in a random motion. They are just moving everywhere. And this motion, I mean, it's like basically kinetic energy. The motion means like you have a velocity. If you have velocity, it means you have a kinetic energy. Okay? Electrons are in a random motion. Even if you don't have any battery connected over here. And the electron gets a velocity over here. And how this electron in an atom or in a wire gets a velocity? Any one of you guys know? I just spend 5 minutes and then finish the class. Any one of you guys know? The electron inside the wire or like a metal piece, they are always in a random motion. Why? From where they get energy? Because motion means I'm moving. Because my body, provide the energy to move. You have a velocity. There should be some source. If you don't have any energy, you cannot walk. You don't have a motion. The electrons are always in a random motion. And from where they are getting that energy? Kinetic energy. Anyone of you guys know? Even if you don't know, that's fine. It's called thermal energy. The temperature, if I have I can give an example because I told you that I can finish this topic in a second, but I want to know you guys understand. Okay. Let's say you have water over here. So at room temperature, the water is like a boiling, but you cannot see that well. If you apply the heat, you provide the flame using like some stove, then you can see that water molecules are jumping. They're jumping randomly. Because the thermal energy provides the water molecule to move randomly. You can see how the water molecules they are jumping. Whenever you apply the energy, this energy is called thermal energy. Okay, I don't know how many of you guys know. The thermal energy is given by 3/2 kV. Okay, T is the temperature. If you raise the temperature this one, then you have a more thermal energy. That makes the electron to move. So now each electron, they are moving. Whenever they move, they collide each other. They collide the wall of the this wire. They are in a random motion. They are moving everywhere. The current flowing through the wire is given by I equal to a net flow of charge divided by time. Okay, I can write down net flow of charge. Net flow of charge divided by time. That means electron has to come from here to here to flow the charge, to make a current flowing through this wire. But here, if you do not have a battery connected, the electrons are in random motion. And random motion is same as the random motion of, like a drunk person. And they compare with that, and I'm not saying that, it's like exactly same. Have you seen like some people, they are really drunk, so basically, I just go like 2 steps forward and come back. Or like go random direction. But I'm reaching nowhere. I'm reaching nowhere. I'm trying to come from here to here, but I'm reaching nowhere. So that net flow of the current, whenever there is no battery, is 0. The electron cannot come from here to here. Okay? Now, the story will be different whenever you apply the battery. Whenever you have a battery connected, it's the positive terminal of the battery, negative terminal of the battery. So this is positive side. You have positive side over here. And it's a negative side. And electron is negative charge. Whenever you connect the battery, now electron knows where to go. Because the negative charge and positive charge, they attract each other. Okay? So now, even if you are hitting with another electron, ultimately you know that where to come. So electron basically wants to come over here because it's a positive terminal. So this is exactly like, you are drunk and you know where to go. You know where is your house. So no matter like this, but I know where to go. Okay? So this is the reason that if you have no battery connected in a wire, you have a net current is 0. But if you have a battery connected, the electron knows how to flow, where to go. So you have a non-zero current going through the wire. So I'm going to continue this one in the next lecture. And this lecture is going to be very interesting. So see you on Wednesday.